Exercise 3b, 7i, you have a function f of x is x plus cos x. It's taken from the book here. The question is, when are we increasing, decreasing? The process is to find the derivative, draw the sign diagram, and see where you get positive slopes, right? But the process could also be just draw the function and have a look at it, which you can do on your calculator. Now, I've tried to do that. Let's see. The view that I got was okay. I did zoom trig. Zoom trig, it spaces out the x-axis nicely. Like I've said it on another video, these spacings are no longer 1. That's pi on 2, that's pi, that's 3 pi on 2. But it doesn't give you a whole lot of window up and down. You might want to, look a bit higher and see. Oh yeah, look, it's going up. That's what you'd have to do in a test, is play around with that window. What I can do is I can look at it on Desmos. So I've drawn it here. Nice and easy to look at this function. It goes up forever, and it shouldn't really be too surprising. If you think of this function is built from like a y equals x and a cos wave. All right, so what's happening is those two outputs, the blue and the green, the y values are getting added together. I've put on, let's look what happens when we put pi in, right? So if I put pi in to the cos curve, it ends up being -1. But if I put pi in on the y equals x, it would be 3.14. And you can see that over that space on the green, yeah, it went down. It decreased by 2, but in the same space, the blues caused it to go up by 3.1. So the blue takes over in terms of increasing, decreasing. And what I mean is that overall it's gone up more than it's dropped. And you can see it in the number there. So it's 1 less than pi, 2.142, 3 decimal places, right? Which you can see there, right? I could change that to 2 pi. It gets me up to here. So what's happened there? That we've got the 1 coming from the cos. That's 1 above the x-axis, which is actually the same level that it started on. And then the blue line, you can see it here. The blue line is just y equals x, so that would be spitting out 2 pi, right? So I'm looking at, here's the function f of x equals x. So if I ignore the cos x, I've just got the blue line where y equals x. I put in 2 pi, I get 2 pi. I put in 2 pi to this part, I get 1. So it ends up being 1 plus 2 pi, right? Anywho, that's what the function looks like. The cos isn't, cos always has to lie between -1 and 1. It's not going to be enough to ever make this red line go downhill. Yeah. So it's always decreasing, although it looks like it goes to 0 there and there. So it has stationary points, but they're stationary points of inflection, and it's going up all the time. And I would say it's always increasing. Anyway, let's do the derivative and have a look at that as well. So derivative equals 1. Derivative of cos is minus sign. To find any stationary points, we would say derivative equals 0 when 1 minus sine x equals 0. Now that can happen, but it's worth noting that cos and sine, let's maybe write this off, both of these, cos and sine, whatever you put in, whatever you make your x, the algorithm, it's going to spit out some value between -1 and 1. That's where those functions cycle between, right? So yeah, I can make this thing 0. I can find an x value. We could rearrange. We could say the derivative equals 0 when 1 equals sine x. So where does sine x equal 1? I could draw a little unit circle. I know when sine x equals 1. It's here. See it on a unit circle, so that's pi on 2. So I could say, well, when x equals pi on 2, and then I could keep going around the circle. Okay, 5 pi on 2. Go around again. 9 pi on 2. I could put those values on a sine diagram. So let's do that. We'll just put 3 on. But what you're going to find is between these stationary points, it's always going to be positive because we've got points of inflection. Now I'm confident of that because I've seen the function, but and you could too. If you were answering this question, you could graph it on your calculator, even in a test. But we can test, in this region here, what if we make x equal to 0? I just want to label these. Okay. We make x equal to 0. There's our derivative. Where is it? It's up here. There's our derivative. 1 minus sine of 0. Well, sine of 0 is 0. You can see it there. So it'd be positive, right? And then maybe look in here somewhere. Let's go halfway. 3 pi on 2. Sine of 3 pi on 2 is -1. It doesn't matter where you pick. Probably be easier just to pick 4 pi and then it's 0 again. But let's say we picked 3 pi on 2 and we put that in. 1 minus sine of 3 pi on 2, well, that's -1. So it's 1 minus -1. It's positive. And then here it would be positive, here it would be positive, no matter what I pick. So these are all stationary points of inflection. Now, because the function is continuous, we can just say that it's always increasing. I know it's sort of somewhat arguable because the slope does go to 0, but we say, well, because it's a continuous function and it's only 0 for an instant, we just say it's always increasing for any x value. X belongs to the set of real numbers, right? Or if you want to write it like, if I'm writing infinity, just use smaller than. So we could say x lies between negative infinity and positive infinity. That's another way of saying the same thing. So it's never decreasing. Never decreasing, that's for sure. Right? Slope's never negative. So don't forget that you have that calculator tool and you can see these functions. You don't have to do everything just from the derivative. Okay, thanks.